Section 17.4, Solubility Equilibria. If I have a test tube with some water in it and I've got some calcium fluoride, so that's the stuff in here, this is calcium fluoride, and it's a solid, and it's dissolving into the water. Remember, some things dissolve very easily. It's in the swimming pool, and some things dissolve very not easily. These would be the things outside the swimming pool. But if it's going to dissolve a little bit either way or a lot, so it's going to dissolve into the solution. So you're going to have some calcium, which is 2+, and some fluorine, F-, as it dissolves. Eventually, it's going to reach a place where the calcium and the fluorine are going to start attaching together again and forming solid, and then coming back into falling out again into precipitate. So you eventually reach an equilibrium. Because you can have equilibrium, you can make an equilibrium constant, which is based upon the concentration of the product. So we have the concentration of calcium ion times the concentration of fluoride ion raised to the second power, okay, because it's got a coefficient. And normally it would be divided by the reactants, but in this case we've got a solid. So remember, you're not going to involve solids and liquids, pure substances, in your equilibrium constant. So that means that the equilibrium constant is equal to the concentration of the two ions in solution. Well, this is an equilibrium constant, but we have a special name for it called the solubility product, because it's essentially the product of the two concentrations of the ions that are in the solution. But the K sub SP is like all Ks. All these Ks are equilibrium constants. So again, K sub SP is called the solubility product constant, or just the solubility product. Okay, somebody was really smart when they made this slide, because they basically gave every possibility. It just is complicated for no reason. If you have a salt, and you remember, if I were to have, let's just say, a salt. So I've got aluminum, which is 3+, and I'm going to combine that with oxygen, which is 2-. And I wanted to find out what the formula was. Remember that this 2 can become the subscript here. This 3 can be the subscript here. So if I were to have Al2O3, okay, then that means when it breaks apart, I'm going to end up with Al3+ and O2-. Okay, so when it breaks apart back into ions, that's how you do it. This becomes the charge of this O, this becomes the positive charge of this A, and this is what you're going to end up with. So that's what the M and the X are for. Well, so here's the N raised to that port, and here's the Y raised to that port. So the M and the X here are the coefficients of that solubility, okay? So you're going to have the balanced equation. So here is a solid that's going to break apart into so many of the positives and so many of the negatives. Well, those are the coefficients that raise to the power here. So I think rather than just trying to put your brain around this, just do some examples and it won't be so hard. So here's an example. If you have calcium fluoride, which is a solid, it's going to break apart into its ions. Well, here's the first ion, which is 2+. It's in group 2. And then I'm going to have 2 of the fluorines. Well, fluorine is in group 7, so it's going to be -1. So when I do the equilibrium constant, I'm going to have the concentration of calcium, okay, concentration of calcium 2+, and I'm going to have the concentration of Fi- or F-, and it's going to be raised to the 2 when you do the K sub SP in a second. Well, let's say that at any point in the experiment, I take the concentration of these guys. Okay, so I just stop the experiment, I measure the concentration of calcium, I measure the concentration of fluorine. So let's say this is at a point somewhere, okay, this is at equilibrium, and so I've got a concentration of equilibrium, I have a concentration of equilibrium. So the K sub SP, if you know the concentrations of the different ions involved, is simply going to be calcium raised to the first power, since it's a 1, and then fluoride raised to the second power, since it's a 2, stick in your concentrations, and you'll end up with a case of SP, which is really just an equilibrium constant of dissolving. How much does it dissolve? How likely is it to dissolve? And remember, with any K, you're looking for big numbers and small numbers. Big numbers is going to tell you you're going to have tons of product. Little numbers are going to tell you you don't have much product. Okay? Well, let's look at this and see, is this dissolvable or not? So I'm going to look. It's got 3.4 times 10 to the negative 11. Okay, negative 11 means I've got 0.00000, 10 zeros before I get to the 3. Can you see how tiny, tiny, tiny that amount is? That means I'm going to get almost no product at all. So a fluoride is not soluble in water. Now, of course, it's slightly soluble. Everything is slightly soluble. We can consider that to be insoluble because it's not going to dissolve like salt, like table salt will dissolve in water. Okay, so you can use your case of SP to indicate whether or not it's soluble. Okay, because it's not going to form very much of it. So here's a table giving case of SP or solubility products of various ionic compounds at room temperature. And you're going to see that some are very, very insoluble. This is aluminum hydroxide. It's just basically going to float on the water. And then some are more soluble than others, but still very, very, these are very slight. You're going to see that it depends. Remember, when we looked at the swimming pool, it depends upon what is in the swimming pool and what's not in the swimming pool. The things that are on the outside they're not soluble. Like carbonates, they're not soluble. This was the coal on the top of it. Remember, the sulfate is the yellow lady. Only certain things are soluble. Silver was one of the exceptions, so it's not soluble. So you're going to get all these very tiny numbers, which shows insolubility. Now, there is a difference between solubility and the solubility product. The solubility is an amount. It's the concentration of this stuff that's dissolved. Okay, so if you have a solid in the bottom of the test tube, and at the end you've got a little bit of that that's broken apart into ions floating in the water, then some of it's dissolved. And I can measure the concentration of that something, such as this magnesium, and it would be the solubility. It's how much stuff you have in a liter of stuff. Okay, so how many moles of stuff do you have in a liter? That's a concentration. So when you want the molar solubility, you're looking for the concentration of one of the ions. All right, so let's look at an example. If I were to have magnesium fluoride, and it breaks apart into magnesium and fluorine, or fluoride, and remember the balance equation is going to be, since this is 2 plus, this is -1, so I need 2 -1, so it'll have a coefficient of 2. For every mole of this, I'm going to get 1 mole of this and 2 moles of this. So this is going to be the amount of concentration of your MgF2, which is the same concentration as your magnesium. So if I can solve for this X, I'll know also, these two numbers are the same, I'll know the concentration of the magnesium fluoride. Okay, so if you're trying to find this, they'll give you the solubility product. This can be looked up in, I think it's Appendix D in your book. All of them at room temperature, different ions, different salts that will break apart. So if the case of SP is 7.4 times 10 to the 11, that's going to be a concentration of this times the square of the concentration of this. Well, here's X. Okay, here's X. This is 2X. Now put it in the equilibrium constant, and you'll end up with X times 2X squared. Okay, that's 4. That's 4 times X cubed. 4X cubed. So 7.4 times 10 to the 11 divided by 4, and then take the cube root of that, and you'll end up with a concentration. And this is the concentration of your magnesium, which is also the concentration of your magnesium fluoride. So how soluble is magnesium fluoride in water? It has a solubility of this concentration. You're going to have this concentration of salt dissolved in a liter of water.